afternoon, good evening, whatever the case may be. We are back and better than ever. And today we are talking about related rates. And we're going to use, the calculus to determine the related rates. So let's get to it, shall we? All right, we'll revisit primitive radio gods in just a second. So what are we talking about? Well, let's consider a ladder that's leaning against a wall. The top of the ladder is at B and the bottom is at A. And the ladder is slipping down the wall. So the rates that are related are how fast the top of the ladder is going and how fast the bottom of the ladder is going if it's slipping. So you can see as it slips down the different positions. We have a right triangle. The relationship here would be, if we let, of course, the horizontal be x, vertical be y, x squared plus y squared is equal to 5 squared. And if the ladder is sliding down the wall, well, the position of B is changing. And we configure or calculate the rate of change using the derivative. So if we get this equation and we take the derivative with respect to time, then we get 2x dx dt plus 2y dy dt is equal to 0. So let's say we were trying to solve for the rate at which B is moving down the wall. Well, that would be the change in y with respect to time. So we could then solve for dy dt if we have enough information to do so. Same thing with x. If we were looking for how fast A is moving, then we would be solving for dx dt. And here they just simplify it. Some obvious things here. Dx dt is a rate of change in x with respect to time t, and the speed of A relative to point O. Here is point O right here. Dx dt is positive as x is increasing. Even though it's moving to the left, the length of x is increasing, so the change is positive. Whereas if B is moving down, the length of y is decreasing, so therefore it would be negative. Okay, so some nice tips here. Problems involving differential equations where one of the variables is time t are called related rates. And the method for solving the related rates problems, pretty straightforward. You always want to draw a nice picture of the situation. Make sure you have a handle on it. You want to write down the information and label the diagrams. And you need an equation connecting the variables. And so really what you should identify first is what it is that you're solving for. What changes you're solving for. And then make sure that's included in your formula. Most of the time, we're going to use the Pythagorean theorem, similar triangles, SOHCAHTOA, right angle trigonometry, sine and cosine rules. We're going to differentiate with respect to t, and this gives us a differential equation. And then we solve for whatever we need to, depending on what they're asking for and what we're given. So I'm just going to move back real quick. These equations are called, I didn't say it before, it's called a differential equation, and it describes the motion of the ladder at any instant. Okay, let's do an example. 5-meter long ladder rests against a vertical wall with its feet on horizontal ground. So before I do anything, I'm going to draw a quick sketch of that. So we have the ground. Oops. We have the ground. Let's make this the wall, and we'll make this the ladder. Okay. The ladder is 5 meters long, so I have that. The feet on the ground slip, and at the instant when they are 3 meters from the wall, they are moving at 10 meters per second. At what speed is the other end of the ladder moving at this instant? So the feet on the ground slip, and so we're talking about this is the one that is moving. So 10 meters per second is describing the speed of this part of the ladder. So let's go ahead and label it. Looks familiar, hopefully, from the explanation I gave at the start. We'll call this A. We'll call this B. It's a right angle. We can assume that. And we'll call this X, and we'll call this Y. At what speed is the other end of the ladder moving at this instant? So the other end is this. If A is moving this way, then B is moving downwards. So it's the Y direction that's changing. So we're looking for dy dt. That's what we are ultimately trying to solve for. All right, so do we have any sort of relationship where we can include y? And clearly we have the Pythagorean theorem, x squared plus y squared is equal to 25, or 5 squared. And if I differentiate with respect to t, I would get 2x dx dt plus 2y dy dt, and the derivative of 25, or any constant, is 0. Okay, so dividing both sides by 2, we get x dx dt plus y dy dt. And remember, this is what we're looking for. The horizontal change here is equal to 0. Well, now we're going to use the information here. We know that at the instant when x is equal to 3 meters here, wrote it in there, we also know that the horizontal change, which is dx dt, remember the derivative is a measure of change, or gives us the change, is equal to 10 meters per second. And I'll just leave it as 10. We're solving for dy dt, so let's substitute what we know. We know x is 3, dx dt is 10, so 3 times 10, plus y. Well, y is this measurement. Well, we're calculating it at this instant, so we know that x is 3. We got a hypotenuse of 5. It's a right triangle. That's a 3, 4, 5 triangle. Hopefully you know that. If not, you would have to use the Pythagorean theorem to solve for y, and shame on you if you do not know the 3, 4, 5 triangle. So 4 dy dt, and you can see how this is going to turn out just lovely. We solve for dy dt, and we get dy dt is going to be, so negative 30 over 4, which is negative 7.5, and that's going to be meters per second. Notice that it came out negative, which makes sense because the motion is down. So at what speed is the other end of the ladder moving at this instant? The speed is, we don't say it's negative, the speed is actually 7.5 meters per second. And if you recall, first derivative, if we take the derivative of the position of something, we get velocity. Velocity tells us the direction. In this case, it's down, and the absolute value of the velocity is the speed, which is 7.5 meters per second. Okay, we'll make that a short one. We'll do part 2 with the next video. And with that, I am out. Takes off from Baltimore and touches down.